hypothesis is a tentative assumption, which we believe to be true until we have data to believe it is not true. The hypothesis we assume to be true is designated by an uppercase H with a subscript 0 and is called the null hypothesis. The name null hypothesis simply means it is the hypothesis we keep if nothing changes. That is, if the hypothesis test does not give us reason to believe the null hypothesis is not true, we will continue to believe the null hypothesis is true. The hypothesis test is the procedure to determine whether the new data is significant enough to reject the null hypothesis in favor of another hypothesis. We call the other hypothesis the alternate hypothesis and will discuss it further in a few moments. The null hypothesis has two possibilities. It could be true, or it could be false. There are two possible actions we could take as a result of the hypothesis test. We could decide to not reject the null hypothesis, or we could decide to reject the null hypothesis. If at the end of the hypothesis test we decide to not reject a null hypothesis that is in fact true, the test would have been a success. Also, if at the end of the hypothesis test we decide to reject a null hypothesis that is in fact false, the test would also have been a success. On the other hand, if we had decided to reject a null hypothesis that is in fact true, we would have committed a type 1 error. If we had decided to not reject a null hypothesis that is in fact false, we would have committed a type 2 error. In this video, we will only consider the type 1 error. Let's now do an example. Our example will start with a population distribution which has a mean of 90 and a standard deviation of 10. This distribution is plotted here. We will use this to formulate our null hypothesis, which will be that the population mean of this distribution is equal to 90. To test the null hypothesis, we will need to take a sample from the population. We decide on a sample size of 4, and the mean of these 4 hypothetical samples turns out to be 82. Remember, the central limit theorem says the mean of the sampling distribution is equal to the population mean, and the standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of the sample size, which makes the mean of our sampling distribution equal to 90, and the standard deviation of our sampling distribution is equal to 10 divided by the square root of 4, resulting in 5. This results in a sampling distribution that looks like this. Remember that our sample mean is equal to 82 and is located here. The hypothesis test will determine whether we can say the difference is a result of the random nature of the sampling distribution or is the result of the mean of the population being less than 90. If we conclude that the difference is due to the random nature of the sampling distribution, we will decide to not reject the null hypothesis because we believe it to be true. If we conclude that the difference is due to a change in the value of the population mean, we reject the null hypothesis because we believe it to be false. In the event that we reject the null hypothesis, we need to have an alternate hypothesis. Because the sample mean is less than the population mean, we state the alternate hypothesis as the population mean being less than 90. The criterion for the hypothesis test is called the level of significance. We use the lowercase Greek letter alpha to represent it, and for our example, we will set it to 0.025. It will become clear what this number means, but for now it should be thought of as the largest probability of making a type 1 error we are willing to accept. That is, it is the largest acceptable probability of rejecting a null hypothesis that is in fact true, an outcome we wish to avoid. So we set the probability to a low number. Another way to look at the level of significance is, the smaller the number we choose, the greater the difference is required to reject the null hypothesis. We will use the standard normal distribution to do the hypothesis test. Remember that the standard normal distribution has a mean of 0 and a standard deviation of 1. Note that the alternate hypothesis is that the population is less than 90. This means we will be doing a left tail test. That is, we will be working in the left tail of the standard normal distribution. We said earlier that the level of significance is a probability and can be represented as an area under the standard normal distribution curve. We place this area in the left tail because we are doing a left tail test. We need to find the z-score that has an area of 0.025 to its left. Since we are working in the left side of the standard normal distribution, we will find the z-score we need in the negative z-score table. We locate the area here, and then read the z-score as minus 1.96. We will save the z-score here and call it the critical z, and denote it with the subscript c. The area equivalent to the level of significance is also shown here under the sampling distribution. The test z-score is the z-score associated with the value of the sample mean of 82 in our example. Recall the equation for the z-score. Let's review how to calculate it. In the numerator, we have x bar, the mean of the sample, from which we subtract the mean of the population. In the denominator, we have the standard deviation of the population divided by the square root of the sample size, resulting in a test z-score of minus 1.6, which we will rewrite here, and is located here in the standard normal distribution. The area to the left is a probability, and we will now determine what it is. The area to the left of minus 1.60 is 0.0548. We call this value the p-value, and we'll rewrite it here, and is the probability of the sample mean being less than or equal to 82. This probability is larger than the level of significance, which is the largest probability of making a type 1 error we are willing to accept. Therefore, we decide to not reject the null hypothesis, and continue to assume the population mean is equal to 90. Let's see what would happen if the sample mean were even further away from the population mean. As the sample mean becomes less and moves to the left, its distance from the population mean increases. The test z-score also moves to the left, and the p-value decreases. At some point, the p-value becomes less than the level of significance. So if the sample mean were 79, the test z-score would become minus 2.2, and the p-value becomes 0.0139, which makes it less than the level of significance. This means that the probability of making a type 1 error is now less than the largest probability we would find acceptable, and therefore we would be comfortable in deciding to reject the null hypothesis and conclude that the mean of the population is now less than 90. Let's go back to the sample mean of 82. Let's now see what would happen if the sample size were to increase. Remember how the standard deviation of the sampling distribution is calculated. It is the standard deviation of the population divided by the square root of the sample size. So if the sample size were to increase, the standard deviation of the sampling distribution would decrease. So if the sample size were to increase from 4 to 5, the standard deviation of the sampling distribution would decrease from 5 to 4.47. The test z-score becomes more negative and moves to the left, making the area and therefore the p-value smaller. If the sample size were to continue to increase, the p-value would continue to decrease until it once again becomes smaller than the level of significance. So in the case where the sample has a mean of 82, from a sample size of 10, the p-value is less than the level of significance, and we would be comfortable in deciding to reject the null hypothesis in favor of the alternate hypothesis. The point to be realized here is that the significance of the sample mean is influenced not only by its distance from the population mean, but also the sample size.